Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest. Find the number of subarrays where boundary elements are maximum. Though the problem looks a bit difficult from the acceptance ratio, but I would say it's a well balanced hard problem after a long time. If you haven't tried this problem yet, I would strongly encourage you to pause the video and give this problem a try. This problem doesn't require any advanced data structures and can be solved using simple tricks. Having said that, if you approach the problem from the brute force solution, you will yourself be amazed how easy it is to solve the problem step by step. So let's get started. The problem states that you are given an array of positive integer nums and you have to return the number of subarray of nums where the first and the last element is equals to the largest element in the subarray, right? So let's take an example. Let's say this is the array 14332. We have to return the number of subarrays of this array such that the first and the last element of the subarray should be equals to the largest element of that subarray. So like these five individual elements can form one subarray. So if you look at this subarray which contains just one, the first element is 1, last element is 1, and the max element in this subarray is also 1. So everything is equal and hence this is a valid subarray as per the definition. So we'll count this in our result. Similarly, this is a valid subarray, this is another one, this is another one, and this is another one. So we have found 5 valid subarrays. Now one more valid subarray is this, where you can see the first element is 3, the last element is 3, the maximum element is 3 as well, and hence this is also a valid subarray. So in total we found 6 valid subarrays from this array which are satisfying the given criteria, and hence 6 is the answer. You can try out any other subarray. One of these 3 criteria will not be satisfied, right? So hope the problem statement is clear. Now how to solve this? Let's look at the brute force solution itself. So brute force solution would be simple, like we need to make sure that these 3 things are equal. Array of 0 is equals to array of x minus 1, which is in turn equals to the maximum element of this array from 0 to x minus 1, right? So this 0 to x minus 1 is just a subarray of this particular array. Now the brute force solution could be, we'll try out every possible subarray. For each subarray, we'll check if these 3 conditions are satisfied. If yes, we will count that in our answer, otherwise we'll not count, right? So we'll just simply start a loop for L here, and we'll try out all possible R for this L, right? Similarly, we'll try all possible R for this next L, and so on and so forth. For each L and R, you will first figure out the maximum element in this range, and then you will check whether the first element and the last element are equal to the maximum element or not. If they are, you will count this in, otherwise you will not count. So the simple brute force solution would look something like this. You will simply have 2 nested loops. Inside the loop you will figure out the maximum, and finally you will check if max is equal to the left and the rightmost element of this subarray, right? If it is not, you will continue. If both are equal and is equals to the last maximum element, you will increment the answer, right? So what is the time complexity of the brute force solution? Order n cube, right? Because there are 2 nested loop. Inside the 2 nested loop, you will have another loop to figure out the maximum, right? Now one obvious thing to optimize here is this maximum part, right? You don't need to iterate over L and R again, because if you already know the maximum in the range, let's say L to R, to figure out the maximum in the range L to R plus 1, you can reuse that information, right? Because of this reusability, we can avoid iterating over every element in the range again, right? So what we can simply do, we can simply check whether the new element that is getting included is greater than the maximum element or not. And we already know that we want the leftmost element to be the maximum element. So we'll assume that array of L is the maximum element, and if we encounter any element which is greater than that, we'll simply break, because we know if that is the case, the maximum element will not be array of L, and this condition will always be satisfied and will simply continue, will not increment our answer, right? So this is like very simple optimization that you can do to make it order n square directly, right? But order n square is not sufficient because the value of n in this case is 10 power 5. So we have to optimize this as well. Now here comes the important part of the algorithm. We have to reduce order n square. First n is coming from this iteration and second n is coming from this iteration. So if we have to reduce, we have to avoid either iterating over all the L's or avoid iterating over all the R's, right? So both of them are equal. So let's try and see if we can avoid iterating over all possible R. Now first of all, what we are doing inside this iteration, right? So we are not going all the way to n. Instead we are going only to the position where the current element is the starting element is the maximum element, right? In other words, we are only going up till the next greater element, right? That is clear. So from this L, where we are going up till the next greater element. So we will be only interested in these all R's. Any other R greater than equals to this will not care about, because in all these scenarios, if you consider this array, the maximum element will never be 2, and because maximum element will never be 2, we know our condition will never be satisfied and there is no point in iterating over any of those R, right? So that's the very first observation that we have already. Now what we want, let's say you are iterating over this one by one, right? So what exactly you were doing? You were incrementing your answer only when array L is equals to array R. So in other words, what you are looking for is which of these elements is equals to array L. If you can answer this question efficiently, you don't need to iterate over all the R. Okay, just to reiterate, we want to remove this R. Now to remove this R, we need to make sure whatever we are doing inside this loop is something we can do without iterating over all the R's. So for that, we started with figuring out what we are doing with each of these R. So we found that first of all, we are not iterating from all the way up to n. We just want to iterate up to the next greater element. That is clear because we want this L to be the largest one. So this L will be the largest one only up till the next greater element, right? Now for each of these R, let's say this is your R. So what you are checking, you are simply checking whether array of L is equals to array of R. If it is, you will be incrementing it, otherwise you will not be, right? So in other words, in this entire range, if you can simply answer how many elements are there which are equals to 2, that many times you will increment answer. And if that count is something you can figure out in less than order n time, this loop can be avoided, and whatever the complexity of finding out how many elements are there with value 2 in this range is something you will multiply with for this R. So let's try to focus on the subproblem now. The subproblem is, given a range L to R, we have to figure out how many elements are there with value x. In particular, x here is simply array of L, right? So we need to figure out this. If you are new to this problem, I would encourage you to solve for solve a smaller version of this problem, wherein instead of having any number here, let's assume you have zeros and ones, right? Let's say the array is binary, and solve it for this binary array first. Like, given a binary array, give me how many elements are there, in the range L to R with value 1, or how many elements are there in the range L to R with value 0. Try to answer that question first, and if you face difficulty there, I would encourage you to revisit prefix sums. Or coming to this particular problem, you can't apply prefix sum directly here, right? Because if you apply prefix sum, you need to find a prefix sum for 3, That is, you need to build an array which will contain how many 3s are there up till a range L. So let's say you have this array, so you will say, okay, up till 0 I have found 1 3, up till 2 I found 1 3, up till index 2 I found 1 3, up till index 3 I found 1 3, up till index 4 I found 2 3, right? Similarly 2 3 3 and 4. So you have to build something like this, and then whenever someone asks you, okay, how many elements are there in the range, or how many 3s are there in the range L to R, you will simply go into this 3 prefix sum array, figure out the value at L and R, subtract the value of R and L minus 1, and you will get the answer. In this case, you will say 3 minus 1, which is 2. So number of 3 in the range this L to R will be equals to 2, and you can verify that yourself as well. Number of 3s in this range is exactly 2, right? So that's basically the trick. In case you have to found this thing for a single x, right? So for a single x, you can build this array and answer this question efficiently in order one time. But x is changing here. For each of the index, you will be interested in different x. So if you apply this strategy, you need to maintain n different arrays. Like you have to maintain the same array for 2, you have to maintain the same array for 1, and finally you have to maintain the same array for 4 as well. Like how many total number of distinct element here, you have to maintain the same array for those many numbers. So overall, just building this array or just building this all arrays will take you order n square itself, right, in worst case. So even though you can answer the question efficiently, but building this entire thing is taking order n square, and you are doing all of these to avoid order n square algorithm itself. So this will not work. We have to optimize this. So hope the point is clear why prefix sum approach is not very feasible here. So what's the next strategy? So think about this. Let's say there is 3, right? So you know that 3 is at position 0, 3 is at position 4, 3 is at position 6, and 3 is at position 8, right? Now when you were building this array for 3, you were incrementing the values at position 0, position 4, position 6, and position 8 only. But because you have to maintain the value all the way along, you have to fill all of these elements as well, right? And that's where the complexity starts shooting up. Like you have to maintain all of this, so you have to maintain this array as well, and maintaining that will take order n square time. So instead of this, if I just ask you, let's maintain this array 0 4 6 8, and now can you give me how many numbers are there in the range, let's say 2 to 5? Can you give this answer? I would strongly encourage you to pause and think about this. The answer is yes. Why? Because you can simply do a binary search for 2 and you will see, you will get this particular position, right? So you will say all of these elements are greater than 2. Now simply do a binary search for 5, you will see this position. So all of these are greater than 5. So apply the exact same strategy and you will say that, okay, we know that there are 2 elements which are greater than 5. We know that there are 3 elements which are greater than 2. So just subtract these 2. There is just one element which is in between 2 and 5, right? The exact same strategy, but instead of maintaining this entire thing, you are now just maintaining the indexes. And because you just have the indexes, you can't simply go to L and R, like that part you can't do, but you still can do binary search to figure out those values. And once you have those values, you can simply subtract them and you will get the answer, right? So we are doing the exact same thing, but instead of maintaining this entire array, we are simply figuring out the values with this array itself, right? Just to reiterate this for one last time, in this case, when you build this array, you will have 1 here, 2 here, 3 here, and 4 here, right? So we are building this array for 3, the prefix sum array, and all of these will be 1 as well, right? And all of these will be 2 as well, and all of these will be 3, and so on and so forth. Now instead of maintaining this extra 1s and extra 2s and extra 3s, what we are doing, we are saying that we know everything up till here is 1, everything up till here is 2, everything up till here is 3, and then after that everything is 4. So we'll simply do a binary search. For 2, we'll simply say where does 2 lies? 2 lies here. So what will the value? The value would simply be this particular thing. Similarly, where would 5 lies? 5 lie somewhere, let's say here. So the value for that would be 2, and you just subtract them, and that will be your answer, right? That's another way of looking at it. So what is the time complexity now? You are maintaining this array. This array you can maintain for each of these elements. That will just take you order and time, right? Now once you have this array, you are doing 2 binary search, one for L, one for R. So each of these binary search will take order, log, and time, right? So overall, in just order, log, and time, you are able to answer how many elements are there which are equals to X in this range L to R, right? Now once you have this answer, let's revisit the final algorithm one last time. So this is our array where we need to find out the number of subarrays such that the leftmost and the rightmost element is equals to the largest element of this of that subarray. So what you did was you first maintained this mapping of indexes. So 1 is at position 2, 3, right? Similarly 2 is at position 1 and 5, and so on and so forth. So you maintain this mapping, and this mapping you will take help to figure out number of elements in the range L to R with value X, right? So that's what you will use this mapping for. Now you also figured out the next greater element. How to figure out next greater element? You can simply figure out that using stack. We will look at it in a moment, but once you have next greater element and this data structure, now for each of these L, you can simply figure out how many possible valid R's will be there. So let's say for this L, you want to figure out how many valid R are there. So you will first look at the next greater element. So this will give you 7. So basically in this range, 3 is the maximum. So we know array L will be the maximum. That is something we have figured out. Now we just need to figure out how many R will be there such that array L will be equals to array R. And because array L is the maximum, array R will be the maximum as well. So we just need to figure out how many R's are there which have value equals to 3. So what you will do, you will simply go to 3, figure out how many 3's are there in the range 0 to 6, and if you look at here, you will figure out there are 3 3's or 3 values here. So you will simply say 3 possible values of R are there for this particular L. What are those? This is first, this is second, and this is third, right? Similarly, for the next one, you will do the same thing. You know the next data element is 4. So in this range, everything for every subarray starting at this L, array of L will be maximum. That is something you are assured of. So what you need to find out now, how many R's are there which has the value equals to 2. So you will again see how many 2 are there in the range 1 to 3. So you will go to 2. In the range 1 to 3, there is just 1, 2. So you will simply say 1, and you will simply add 1 to your result. And you will keep on doing this for all this L, and finally you will get your answer, right? What is the overall time complexity? Building this array would just take order and time, because you can do this with just one iteration and using a stack. Building this entire structure will take you order and time, depending on how you are building it. It may take order and log n as well. And finally, for each index, what you are doing, you are figuring out number of element which is equals to X in the range L to R. That will take you order log n time for one element, and you are doing it for all the element. That will take you order and log n time as well. So if you sum everything up, the complexity is of the order and log n itself, which is sufficient to pass the given time constraint, right? Now the final thing, if you are not very sure, or if you face difficulty in understanding how to figure out the next greater element using a stack, next 2 or 3 minutes of the video is for you. You can skip that if you already know about that. So the basic strategy is you have to figure out the next greater element of 3, let's say, right? So you will simply maintain all the breakpoints, right? By breakpoints, what I mean is whatever is greater than 3 you will maintain. So currently for last element the answer is simple, there is no element which is greater than 3. So for last element the answer will be 9, right? Now you will simply add 3 to your stack. Why? Because for anything before this 3 can be maximum element, right? So that's why we just put 3 in our stack. Now let's come to 4. We need to figure out what is the next greater element for this 4. So what you will do, you will look at the stack. You say, okay, 3 is at the top of the stack, which means 3 was the maximum element I have seen so far, and current element is 4. So for any of these elements, if I have to figure out, okay, what is the next largest element, would you ever answer 3? Answer is no, because you know there is 4 before 3. So if you have to figure out if 3 is the next greater element, or 3 can never be the next greater element because there is a 4 4 before this 3. So either 4 will be the next greater element, or there is no next greater element for any of these elements at all, right? So in other words, you will simply pop all the elements which have smaller values than this, because those elements will never be the next greater element of any of the previous elements, right? So that's the basic strategy. So now for 4 you popped 3, and once you pop 3 you say there is no more element left, right? And because there was no more element left, no more element left, you will simply say there is no greater element in the right at all. So for this as well the answer will be 9, right? Now you will put 4 again, because that can be the next greater element of any of the previous elements. So now comes 3, let's say. Again the same thing, you will look at the top there is 4, and 4 is greater than 3. So you will simply say 4 is the next greater element. So whatever is the index of this 4, that will be the value here, right? Now after this you will push 3 as well, right? Why? Because this 4 can be the next greater element, but if you encounter something which is less than 3, then this 3 is the next greater element, right? So that's where you are just maintaining all possible next greater elements, and whenever you see anything greater, you pop all the smaller ones, because you know that once you have seen a greater one, none of the previous elements would have the next greater element as the other ones, right? So it's very similar to, let's say, you are standing here and you want to look at some pillars, right? So you can not look at this pillar at all. Like you can never look at this pillar, because either you will look at this or you will look at this, right? You will never look at this. So that's where we are simply discarding all of these types of values in this range, right? So that's the basic strategy. You will simply keep on doing this, and this array will be built in just order and time using a stack, right? So if you have watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself. The code would be very straightforward, and try to get it accepted as well, because that's the most important part while you have solved. So next we're looking at the code. The code is what we have discussed. We first build this indexes array or indexes map, this entire thing. Once you have this, we also build the next greater element using a stack. As discussed, we'll simply keep on popping the elements until if it is less than the current element that we are looking at. And finally we look at if the stack is empty, there is no element which is greater at all. Otherwise, that whatever is the top is the next greater element. Now once we have the next greater element and this, we'll simply iterate over all of these and figure out for this L, this is the maximum R that can be possible. So how many nums of st is present in the range L to R. That's what we need to figure out, and we'll simply add all of them, and that will be our answer. Now count between is simply doing two binary searches, one for L and one for R, and simply doing L minus R minus L, right? So hope this entire session makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already.